Got it? You don't do the big, that's it, okay. Classy. So let's do number line. If I had 50 grams of one and 50 grams of the other, they're going to meet in the middle, right? And what's going to be the answer? B. Exactly 50. Right here, 50 grams, 50 degrees. Good? Okay. Everybody got that one? Let's take a look at the next one. See if Barbara can get this one right. I'll call her out on video. Who's got this one? So again, we're going to go back to, if we started out with 50 grams of water at 80 degrees and 100 grams of water at 20, right? Where did we end up at the end of last time? 50. So imagine that I started off at 50 and then I added another 50 grams of water at 20 degrees. That's going to make it colder. So it's going to be between 20 and 50 degrees. I don't know exactly how much. You could figure it out, but, right? So you'd have to figure it out, but yeah. Okay? Does that make sense? You okay with that now? All right, cool. Let's take a look at the next one. I got a 50-gram sample of water at 20 degrees. I went the wrong direction, didn't I? Nope. Oh, there we go. Yeah, I got a 50-gram sample of water at 20 degrees. To it, I add 50 grams of iron at 80 degrees. Figure this one out. This one takes a little more thought process here. Everybody got an answer? What did we get? You got C between 50 and 80? So I have two different substances here. One of them is what?
Water.
And one of them is iron. What's the specific heat of water? 4.184, right? And the specific heat of iron? It's pretty low. It's less than 1. I don't remember it exactly, but it's less than 1, right? So I love the way one student said it. That is, when I add iron to the water's at 20 degrees. The water is going to cool off the iron faster than the iron is heating up the water. Because the iron has a low specific heat, right? That means it has a lower capacity to hold heat, too. Water, on the other hand, with 4.184, has a higher heat capacity. It takes energy to heat it up, and it also takes, it has to release a lot of energy to cool down. So this little bit of iron is not, at 80 degrees, is not going to change that water nearly as much as the water is going to change the iron. Y'all follow? You get that now, specific heat. So specific heat really matters. All right, cool. Let's now talk about Hess's law, our good friend Hess's law. We probably touched on this last year a little bit. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. And in fact, what you're going to learn in chemistry is that most reactions that we talk about are actually series of steps. Even something as simple as dissolving a salt in a water is multiple steps. Oh, yeah, Big Mama's is good. You got to know that.
Also known as Hess's law?
Yeah.
I mean, there's something else I explained.
Yeah, so I'm going to be doing this one. So even something as simple as, which is the experiment we're going to be doing next class, assuming I can get all the pieces put together. If not, we'll push it to the following class. But so if I were to dissolve salt into water, right, the simple thing, right? Not a giant chemical crazy reaction here. We're just going to put salt in water. Well, what has to happen first is the salt has to break apart. Then we have to make bonds with the water molecules. Then things have to get pulled apart. It's a multiple step. And like a lot of things, we've talked about this being a state. I'm going to start up here. I'm going to have a reaction that brings me down to here. I'll have another reaction that does this, another reaction that does this. Okay, another reaction that does this. Okay. All I care about is this final difference. That's what I care about. I don't care how we got there. I care about products minus reactants. Where did I end up? Where did I start? That's what I care about. Good? That's the important thing to take away from this. All right. The best way to talk about Hess's law is to start looking at things. If a reaction is reversed, so one of the things that we're going to talk about in chemistry that we probably have already talked about is that many reactions go both directions. And in fact, we talked about this, I told you all this last year when I talked about physical chemical changes. One of the reasons I don't like the concept that chemical changes don't go back and forth, because in most cases, I can reverse a chemical reaction. I may have to do something strange. I may have to add energy to it typically. I can actually drive or add heat, right? But I can drive a reaction one way or the other by altering some pieces of it, okay? And when I do that, I reverse the sign of the delta H as well. The magnitude of the delta H is directly proportional to the quantities of the reactants and products. So it's what kind of property? Extensive, intensive. Extensive or intensive if it's directly proportional to the quantities of the products or reactants. If I add more stuff, it's extensive. If I add more stuff, I get more heat. That's going to be an extensive, right? If the coefficients in a balanced equation are multiplied by some integer, then the value of delta H is multiplied by the same integer. We looked at this last time when we did some stoichiometry, right? So if I say that A plus 2B yields, let's do this, yields 3C plus, let's say, 136 joules of heat. And this is one way I want you all to start thinking about this. This is an exothermic reaction. Do you understand? I put these two things together. I got 3 of these plus the heat. An endothermic reaction would be like this. Okay, that's on this side. In order to make this reaction happen, I had to put some energy into it, endothermic. If I treat them like that, then when I multiply this, if I said, well, what happens if I have 2A and 4B? Let's multiply the whole thing by 2. I get 2A plus what? 4B yields what? 6C plus, what's that? 170, 272. There we go, 272 joules. Am I allowed to do that in algebra? Chemistry is just expanded algebra, right? So if you do good in algebra 1, you can do good in chemistry. Okay, same thing. Just expanded algebra. As long as I do it to both sides, it's totally allowed. That's all we're saying here. Let's try not to make that too complicated. That's all we're doing. We're saying if I multiply this, if I multiply all this stuff, I also have to multiply this because it's part of the reaction. All right. Let's talk about some problem-solving strategies. First of all, we're going to work backwards from the required reaction. We're going to figure out the reactants and products to figure out how to manipulate everything else. All right. Reverse reactions is needed. If I'm going through multiple steps, we actually in chemistry have written out a bunch of reactions with sort of stock. We said, okay, if we have one of these and one of these, I'm going to make this much heat. Well, what if I, instead of having one of these and one of these, I make one of these and one of these? I can take the whole reaction and flip the whole thing. Totally legal, right? Totally legal. We're going to multiply the reactants to give however many numbers, the numbers we need. This is kind of similar to what we did in some of our other reactant balancing, right? We just finished, what did we do? Well, we needed to adjust electrons and multiply. Y'all remember doing that? Same kind of thing. Same kind of thing. So we're going to do a similar situation here where we're going to get rid of, we're going to have to multiply so we can cancel things out. Let's take a look at this. Is this? I think this is in your notes. Is this one in your notes? The diborane. It should be right away. If not, no. Grab yourself a piece of paper. This one's worth writing down. All right, so diborane is a highly reactive boron hydride, as you might imagine, that was once considered as a possible rocket fuel for the space program. Okay? So we're going to calculate the delta H for the synthesis of diborane from its elements according to this equation. So go ahead and write that down. You don't have to write all this stuff, just write this, the equation there. We good? All right. These are the kind of reactions that you're going to be given. So I have all these different pieces of data. And notice something odd. This is probably the first time we've run into what? Fractional moles. Okay? Here's what this says. I am still good. This is talking about the amount of heat. Is that absorbed or generated? Generated, because that's a negative, right? So the amount of heat generated when I make 1 mole of this. All right? The rest of this, it all has to balance to be 1 mole of product. Same thing here. I'm looking at this. If I'm making 1 mole of this, I'm going to generate this. If I'm making 1 mole of this, okay? If you all remember, I take hydrogen and oxygen and I ignite them, combust them together, and they make water, and in doing so they produce heat. That, we all remember that, right? I need to demonstrate that again. Also notice that if I go from liquid water to gas water, I have to release heat, 44 kilojoules worth of heat, in order to move 1 mole of liquid water to 1 mole of gas. I have to bring in 44 kilojoules of heat. What are we doing with these pieces? So I guess we're going to have to walk through these. Good? Okay. Here's how this works. Okay. To obtain the delta H for the required reaction, we must somehow combine all these reactions. This is going to require us to rearrange the reactions, to multiply the reactions times integers, okay, until we can basically cancel each other out and end up with the net reaction. Right? So that's where we're heading. We're going to start on the reactants and the products. So this is kind of a puzzle. I kind of like Hess's law for the puzzle. Here's my reactants. I've got solid boron, I've got hydrogen gas, and I've got the reactants of B2H6. I mean the products of B2H6. Good? So I'm going to write that down. Reaction A has the boron, the solid, as a reactant as needed for this equation. So we're going to write that out. Just like it is, boron, it's a reactant. Our initial, in fact, let me write that above so we can kind of keep track of what's going on. There it is. I really can't believe this isn't there. Okay, and we're trying to solve for the delta H. That's what we're trying to solve for, the delta H of the whole thing. I don't really think that helped the people at home, but I definitely don't want that one. There it is. All right. So this is my reactant. So let's go to this one. I'm going to start with this equation. And notice in this equation, the boron is on the reactant side. Y'all follow me? And in fact, I actually had the same amount. So I'm going to go ahead and write 2 boron S plus 3/2 O2 gas yields B2O3 solid and minus 1,273 kilojoules. Okay? So now I'm going to take a look at the next thing here. Do I see an equation that has hydrogen as a reactant? Yeah, which one's that? C. So I'm going to go ahead and write C up here, and I'm going to write H2 gas plus 1/2 O2 gas yields H2O liquid and minus 286 kilojoules. Okay? Now, do I have enough H2? How many H2 does this require? 3. How many does this give me? So let's multiply everybody here by 3. Okay? So that now gets me 3 H2 gas plus 3/2 O2 gas yields 3 H2O liquid. And minus 286 times 3 is, yeah, you may want a calculator. What is it? Okay, that takes care of that. Those two guys are covered. Let's walk through this. Oh, yeah, okay. Let's go back here. All right, do I have anything that has B2H6 as a product? No, but I do have something that has B2H6 as a reactant. So I can take this whole thing and flip. I can flip the whole thing. So that means that I'm going to have 3 H2O. Gas, state is very important, plus B2O3 solid yields B2H6 gas plus 3O2 gas. And when I flip this, I also flip the sign. So this is 2,035 kilojoules, and I actually like to put the plus. Okay? I'll blank that just to make it easier for everybody to read. Good? Everybody got this so far? All right. So if we wanted to, we could start canceling, but since I gave you the fourth reaction, that probably is a clue, right? So I notice that I have gas on this side and liquid on this side. Y'all follow? If I wanted to right now, I could start the canceling and I would see a problem. So I'm going to basically solve these, squish them all together. So just like before, these are equal signs. Sorry, I try to keep these lined up, but they're not. Can I cancel this out? Do I see this on the product side at all? So that's going to stay. What about this guy? Do I see oxygen on the product side? Yeah, if I saw oxygen, so I can cancel this 3/2 oxygen with this, right? I can get rid of that. That leaves me with, we okay? Just algebra. How about this guy, this B2O3 solid? Do I see that on the reactant side? Where do I see that? Right here. So these guys can cancel. And then I'm just going to come down here. What about H2? 3H2. Can I cancel that? No. What about 3/2 O2? Yeah, I can get rid of that. Get rid of this 3/2 and this 3/2. Takes care of that. Okay. What about 3H2O liquid? Can I cancel that? No, because that's a gas and that's a liquid. So this is where we are reminded that state matters. And so I need to write this in such a way that liquid's on this side and gases on that side. So I'm going to have to add H2O, liquid, yields H2O gas plus 44 kilojoules. What do I need to multiply that by? I need to multiply this whole thing by 3. I'm not flipping it, so I just multiply it in place. It gets me 3 H2O liquid, 3 H2O gas, plus what? 132 kilojoules. Okay. So now, going back to my situation here, do I have 3 liquids on the other side. So I can cancel these and these. And what about the gas? Cancel the gas too. And now let's see, do I have my 2, let's go back up to the original. Do I just have 2 boron on this side? Right? And I just have 3 hydrogen on this side. And I just have B2H6 on this side. Everybody okay with that? Now what I will need to do to answer this question, we're going to add these together. This plus this plus this plus this. So y'all, if you need your punchy, go ahead and get that out there. 36. What is it?
36.
36?
Yeah.
Like 3, 6?
3, 6.
Everybody agree with that? So remember, y'all should all check your work. You get your punchy out and add them together. I'm going to use the green marker so people can see the canceling a little bit better. Is that what you got? Where's your calculator? You didn't get that. You're just trusting your friend. You should never trust your friend. What'd you get? Okay. What'd you get? Really? Good. Do y'all see how that works? It's kind of a little fun problem solving.
It's just a lot. Yeah.
It's not that hard.
In a timed test, it is.
You know, this
Like,
isn't
it's
going to be on
easy.
the test. It's going to be on stuff you don't understand.
Yeah.
This is like,
If it's like that.
Yeah, this is FRQ stuff.
This?
Yeah, so
I mean,
you'll
my
have,
test is like how it was last semester.
yeah. Well, y'all will get better, and we'll get you trained to know how to take tests.
Not like that.
Yeah. Well, that's true. It won't be like that. Instead of having 2 minutes a question, you'll have 90 seconds a question.
Oh, even better.
So you're right. It won't be exactly like that. All right. We're just training. You're getting what?
My refund.
Okay. Yeah, oh yeah, by the way, if you need to sign up for not just my class, but any class, go ahead and take care of that today. Go ahead and pay for that today. You can avoid your late fee. Remember, if you avoid your late fee today, that's okay, because you can get a refund come February, March. I don't know when the deadline is, but go ahead and pay it today. Get registered, and then, because I'll be willing to sit down with you and give you an honest assessment about your chances. Okay. I mean, I think most of y'all, in fact, everybody who's in this room, if you're in the room physically with me here, you can get a 3. Some of y'all can get 4s, some of y'all can get 5s, but I think everybody can get a 3. The honest thing you need to do, though, is look at the universities you want to go to, because a lot of them don't take 3s, right? So they'll take a 3 for college credit, but they won't necessarily take a 3 for that chemistry class. So they may give you some elective 3 hours of credit for it and still make you take chemistry, which is fine. You save about $2,000, which is fine. You just need to make sure that they're willing to give you some credit for that. So the private universities like the one I went to only take 5 for chemistry. I didn't take any AP courses.
Wow.
So it wasn't, they weren't offered. I went to a little bitty school. Stuff wasn't offered. I actually did in geometry. I taught the geometry class. All right, here we go. All right, so as we did up on the board, and 19 slides later, they did the same thing. Y'all see how easy this is? This is straightforward. It's just a little bit of fun problem solving. Y'all good? Okay, so this takes care of our reaction. We're going to ask you to solve a problem like this and give you the base reactions, the reaction to either heat or heat required or heat produced by a particular reaction to generate 1 mole of product. And that's why we see those weird fractional moles in our balanced equations. And you're going to see more of those as you keep going in chemistry. All right. So the delta H for the synthesis of 1 mole of diborane from the elements is 0.36 kilojoules. All right, here we go. Is this one on your notes? Hopefully it is. Oh no, this is a test. If I take solid sulfur and oxygen and I make sulfur dioxide, I release 296 kilojoules. What is true? Which one of these are true? 1, 2, or 3? So again, pick up your pencils, make some choices.
Wait, could it be more than one?
Sure.
Is that a statement?
Sure. It's one of those 1, 1 and 2, 1, 2 and 3, 1 and 3 but not 2. There'll be a lot of these on our next test, so I love these. These are fun. Right. So on these, I would just like sketch down real quickly. 1 is true, 2 is true, 3 is true, or 1 is false. So just like make true or false. Like 1 is false, 2 is false. Okay. Good? You got something sketched down? Cool. So who thinks 1 is true? Why? Negative sign. Who thinks 2 is true? Because we divided everything by 2, right?
Yep.
Okay. Who thinks 3 is true? What's going on with this one? So 32 grams happens to be what? 1 mole. Good. And all I did here was what? I converted to joules from kilojoules. Good? We all good? Cool.
Right, to do the kilojoules, and then the kilojoules go down to the bottom. 1,000 kilojoules.
So this is 296 kilojoules,
Yeah.
and then I'm going to bump it 2 more. So this,
Okay.
so it's 2.96 times 10 to the 5th joules.
You divide by 1,000.
So we divide by 1,000. That got me, so 296 joules. I need to convert 296 to scientific notation, or 296,000. So 296 kilojoules, right?
Yeah.
So that's 296, 1, 2, 3 joules. And this is 1, 2, 3, 4, 5. 2.96 times 10 to the 5th joules. Good?
Wait. How do you do the second one? You said you divide by 2.
This one? 1, 2, 3, 4, 5.
No, the 2, like the.
This one to here? Oh, the second. You mean the second question?
Yeah.
This one. All right. So this is true if I start with 1 mole of sulfur. I multiply the whole thing. If I change this, I have to change everything because algebra, right? So I'm multiplying the whole thing times a half.
So 296 divided by 2.
It should be 148.
Got it. Thank you.
Good? All right. Standard enthalpy of formation. That's what this little F means. All fixed? No. So, this change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. All right. The degree symbol on the thermodynamic function indicates that the corresponding process has been carried out under standard conditions. Standard conditions are not STP. Standard conditions is 1 atmosphere and 25 degrees Celsius or 298 Kelvin. Standard conditions. That's when I talk about, if you look in the periodic table in the back, you see some things are blue, some things are black, and some things are red. The red means they're at a gas, blue is liquid, black is solid, under standard conditions. See those? Those. Red, gas. Sulfur, these guys are solid, these two are liquid. The white ones are man-made. Okay, so standard state. All right. Whoa, there we go. So standard state for gas is 1 atm. If you're pure substances in a solid state, the standard state is either the pure liquid or the pure solid. If we're talking about a substance in solution, we're talking about a 1 molar solution. So if I say something's in standard state, aqueous, it's 1 molar. All right. Standard state of the element is the form in which the element exists, 1 atmosphere, 25 degrees Celsius. So oxygen is a pressure of 1 atmosphere. Sodium is the solid sodium. And mercury at 25 degrees is liquid. That's what we just said. All right. The enthalpies of formation. So ammonia gas is negative 46. Here's some examples. Water, negative 286. It's the amount of energy that it takes to form water from hydrogen and oxygen. Because water is not an element on the periodic table, right? So if I start with hydrogen gas and I start with oxygen gas, what's it take to form liquid water? All right. When a reaction is reversed, the magnitude of the delta H is the same, but we flip it. And when the balanced equation for a reaction is multiplied, we have to also multiply the delta H. That's what we kind of did just a minute ago. What I said was the sum of the reaction is the sum of the enthalpy for all of the products minus the reactants. You're going to see this over and over and over. It's final minus initial. All right. So, like other things, it is, like I was just saying, it is final minus initial. In this case, products are my final minus my initial reactants. So I'm going to sum all of the enthalpy for the products, sum all the enthalpy for the reactants, do this single step, and we're good. This is the important point, that the enthalpy of formation, that's F degree sign, for a state, element in its standard state is 0. So the elements as they appear at 25 degrees is 0. If I'm just talking about O2, it's 0. Because remember, O2 is what it is in its standard state, right? Okay. Using enthalpies of formation, calculate the standard change in enthalpy for thermite, the thermite reaction. We should be able to do that this year. Okay. So I've got some aluminum solid and our good friend iron 3 oxide, rust, mix them together. We end up making aluminum oxide and some solid iron. It's actually very useful. You can actually go onto YouTube now and see some cool videos. It's how they weld railroad tracks. So they get them real close to each other, and they pack it with this stuff and start this cool reaction. This reaction occurs when a mixture of powdered aluminum and rust is ignited. It takes a lot of heat to get it started, but once it does, it takes off. All right, let me go ahead and write that equation up. So this is 2 aluminum solid plus This one you should have? Okay. Page 8. Page 8, exercise what? 10. Exercise 10. We're going to calculate this. This is what we know. Here's our givens. So one more. Yeah, there's our givens. So based on this, can you solve that, please? Here's our heat of formation for iron 3 oxide. Our heat of formation for enthalpy of formation for aluminum 3 oxide, aluminum oxide here, and for aluminum solid, and for iron, these are 0. Yeah, they'll give you whatever pieces you need. Back in the old days, they used to just give a giant table, and so you'd spend some of your time wading through this table trying to find all the data. And that's one of the changes I do like, that they give you what you need to solve the problem. So let's see. This is so what is the sum of the products? So the sum of the products is what? Sum of the products? Right, 1676 minus, what's the sum of the reactants? That's it. We're done. And we should end up with negative 850. Notice they were very careful. Put the little dot. You may not be able to see that on screen. Dot. Sig figs. Okay? So, yeah. Because otherwise, you would think you'd only had 2 sig figs. And, of course, if you needed this to do some future math, you want to keep track of all that. Yeah, this process is so highly exothermic, the iron that is produced is actually molten. It actually melts the iron as it's made, which is what makes it so useful for things like the welding that I was talking about. Yeah, so ships' propellers, railroad ties, all these kinds of things. Very, very, very cool, very useful process. All right. Okay, here's a good problem. Till recently, methanol was used as the fuel in high-performance engines. Using data from the table containing standard enthalpies of formation at 25 degrees, compare the standard enthalpy of combustion per gram of methanol with per gram of gasoline, assuming the gasoline is octane. So you got your textbooks. No, you have a table in your notes, yes. You should have a table that has oxygen and for that's not going to give you what you need. Okay, I guess we'll just watch this one. It'd be better if I thought you guys had that table in your notes, sorry. All right, so we know the standard enthalpies of formation from the table. All right, so we've got methanol. I guess we can watch methanol. So C3, CH3OH, and C8, H18. Okay. All right, here we go. Keep that. There's our combustion reaction using the standard enthalpies from the table. All right, we're looking for the formation of carbon dioxide, we're looking for the formation of water, and we're looking for the formation of methanol. And all we would do is take the values from that table. This is products minus reactants. Remembering that this value is going to be what? 0, because O2, that's its standard state. You haven't done anything to make O2. It just showed up in the universe that way. All right. There we go. So this is methanol's value. We would have looked up the value for CO2 and for H2O, right? And I do not like the parentheses, but I get it. And then,
Oh, we have those numbers.
yes, anytime, what, you have those numbers?
Yeah.
I thought we said we didn't. Oh, they happen to be in that table?
Yeah, we have the CH308, CO2, and water.
Oh, okay. Y'all do have the numbers in. All right. Well, y'all go ahead and do octane then. All right, so given this one, let's go ahead and write the equation for octane. So that's C8H18 plus O2 yields CO2 plus H2O. It's 8 of those guys because of that guy. It's 9 of these guys. Is that right? And then we got to change it, right? Because that's a odd number. Follow? So this is actually going to be 2. And this is going to be what? 16. And this is going to be 18. Okay? And so that's 32 plus 18 is 50. So how many of these do I need? Okay. Let's see if that's right. Looks good. We at least got the balanced equation, right? So given the information you have information about this guy. This guy's super easy. It's 0. I'll do that one for you. 25 times 0. Okay. This is 16. This is 18. And this is 2. What goes here? 2, negative 2 what? 269. And this one is negative 394. Okay, and the water is negative 286. Okay. So I'm going to add these two together. And I'm going to subtract this value, right? So I add these two together. What does all that add up to? Negative what? 11,000 what?
452.
What?
452.
452. Minus, what's this equal? Okay, so that should equal What is it? Minus 10,194. 914. Okay. Did everybody get that? Let's see what the.
I got 7.
Okay. Good job. Appreciate that. Glad you could join us. Glad you could join us too.
You're welcome.
And you too. Everybody okay? Y'all see how that works? Pretty straightforward. All right, so remember this is the heat. Oh yeah, this is a good question. This was the heat when we did 2 moles of octane, right? So in order to get the heat for 1 mole of octane, we need to do what? Divide by 2. Now we want to figure out what is the heat generated per gram. So, because that's what we're checking. We're seeing the difference in the heat generated per gram of methanol versus per gram of octane. So, for every gram of octane, we're generating 47.7 kilojoules. So the enthalpy of combustion per gram of octane is approximately twice that per gram of methanol. All right. Gasoline appears to be superior for methanol for a race car where weight considerations are usually very important. However, methanol burns much more smoothly in high-performance energy, and this advantage compensates for its weight disadvantage, particularly in your drag strip cars, your quarter-mile cars. That's why they used methanol, because it's like I need to go a quarter of a mile really fast. I might as well just use the methanol because it'll keep my engine together. That's sort of an important thing. Your other race cars, the guys who just drive around in circles for 500 miles, they need that. They need some efficiency built into their fuel as well, and they need to worry about that weight consideration. So they're going to use the octane. They're actually using some. They're using a slightly different fuel now, but yeah, they're using an octane, basically a gasoline, because it per pound per mass, it has more energy per mass than methanol does. All right, let's see. Given the following equation, which of these following statements are true? So the same thing here. I would just write 1, 2, and 3, true, false, whichever ones. Okay. Is this reaction endothermic? No. Why not?
Negative sign.
Negative. Is the reverse of the reaction having a positive 75 kilojoules per mole?
Yes.
Yes. Is the enthalpy for H2 0?
Yes.
Yes. Okay. Good. All right. Let's talk briefly a little bit to wrap up some of the energy sources that we use as we move through. We're still not using a lot of hydro and nuclear. We have drastically reduced our coal use. What's that? And we can think about these things. Remains of organisms that lived 500 million years ago. We got a bunch of it. We got plenty of it. Fracking has revealed a whole lot more of it. And so if we need it, it's there. It doesn't mean we shouldn't get more energy efficient and more energy conscious, but there it is. Of course, that's what drives our entire state economy. petroleum and natural gas. Okay, this is natural gas is mostly methane, but it does have some other stuff in it. So when I talk about this, I usually say, "Oh, this is methane." Well, it is, but there's some other stuff in it too. Yeah.
What does the A mean?
Where?
The A and E at the end of methane, ethane, propane, butane.
Oh, or you'll learn that in organic chemistry.
Are we doing that this year?
No, we don't do any. In fact, they cut all of it out. So we stop in ninth edition, actually 10th edition too. I think chapter 18 is our last chapter.
What chapter is that?
Chapter 18.
No, like what is it?
It's electrochemistry. Now we're in the spring we're gonna skip around a bunch. When we come back from Thanksgiving break, I'm gonna back up and we're gonna do a review to make sure we've got all the pieces. Basic chemistry. Talk about photoelectron spectroscopy, some mass spectroscopy, some stuff like that. That's review. It's all stuff that was in chapters 1, 2, and 3 of the textbook that some of y'all apparently during the first 3 weeks of school did not actually study, even though it was assigned. So, yeah, that's the situation. That's why y'all like really struggle on this test, and I'm like, this is basic stuff. This was in the first 3 chapters. Why are we struggling? Oh, because we didn't actually study the first 3 chapters that were assigned. Yeah. Okay. So here's your formulas if you care about such things. Methane, ethane, propane, butane, pentane, hexane, heptane, octane. Really complicated naming structure.